Hi everyone, thanks for stopping by again. This will be DCL 420. I ran into a question on Facebook about antenna gain figures, and I thought, hey, there's a video I can make. So I want to talk about gain and front to back ratio, gain over dipole, all that stuff. We got to talk about all that stuff if you're going to understand antenna gain figures. I'm going to run through this quick. We've got to introduce you to a few topics that'll be a little strange at first. But don't worry, I think I can explain them very simply, which I should be able to because they're actually very simple concepts. If you're really into antennas and SWR and wavelength and all that stuff, check out my playlist DCL 400. There's a link to my major playlist in the description of this video down below. When you go to that, you'll see all the other playlists within the major playlist. You can look for DCL 400 or maybe, well, you'll just see what's in there. So in this presentation, in order to talk about antenna gain figures, we've got to talk about the dB. We've got to talk about isotropic and what it is. Then we can talk about gain in an antenna. And then we can finally talk about what a front to back ratio is. So let's start with the decibel, the dB. This is extensively covered from a mathematical perspective in the DCL 090 playlist. If you're pretty good with math, you probably only need to watch DCL 093. If you're just not interested in all the math, don't worry about it. I'm going to explain to you what you need to know, but not everything there is to know. dB ratios. dBs are ratios of power. Now you can also measure ratios of sound levels and current and voltage, but that we don't care about that right now. So for right now, we're talking about power ratios. If you have a 100-watt radio and you feed it through a piece of coax and you get 100 watts out the other end, that means you have a power ratio from one end of the coax to the other of 1. That's a 0 dB change. See, 0 dB doesn't mean you have nothing, it just means nothing changed. If you put, say, 10 watts into an amplifier and it gave you 20 watts, you'd have a 2-to-1 power ratio. The amplifier gave you 3 dB gain. But if the amplifier is not running right and you put 10 watts in and you got 5 watts out, you would say you have a 3 dB loss, which would be negative 3 dB gain or 3 dB loss, usually written as minus 3 dB. But what if you, okay, let's say you had a 10-watt radio and you put it into an amplifier and you got 40 watts out. That's 40 watt. That's 4 times the power. Well, 4 is a double, which is 2. Then it's a double again for 4. So the first double is 3 dB and the second double is 3 dB. So that's 6 dB. By the same token, if you lost and ended up with 1/4 of what you had, you'd say you had a 6 dB negative gain or a 6 dB loss. So what if you doubled your doubled and then doubled again? In other words, if you had 8 times the power out of the amp. Well, the first double's 3, the second double's 6, and the third double makes it 9 dB. If you ended up with 1/8 the power because the amplifier was bad, you would say you had a 9 dB loss. Now, you're probably wondering about what would 10 times the power be? Because that's not a double. That's just barely an increase from 8 times. 10 times happens to be 10 dB. If you lose and end up with 1/10 of what you had, that's 10 dB or minus 10 dB or a 10 dB loss. If you actually just remember 3 dB and 10 dB, you can pretty much use dB ratios without a calculator. Not perfectly accurate, but close enough. Because if I had 100 times the power, that's 10 times the power times 10, or 10 times 10. So the first 10 power increase is 10 dB. The second 10 power increase is 20 dB. So do you see the difference between a 0 dB and a 10 dB gain? That gave me 10 times the power. But when I go from 0 to 20 dB, I have 100 times the power. Again, dB ratios are based on a logarithmic scale, which makes them actually very powerful. Let's do an example. My radio puts out a watt, but with my amp, I get 20 watts. So what do you suppose my gain in dB is with this amp? Well, we know that first I'm going to go to 10 watts. That's 10 dB. But when I go from 10 watts to 20 watts, that's only 3 dB more. So what is 1 to 20 watts? Well, it would be 10 plus 3. It would be 10 dB plus 3 dB. So my amp's gain is 13 dB. They really are that easy to work with. And as you can see, you really don't need a calculator. Now, if you wanted to get really accurate, if I was going from 1 watt to 17.6 watts, yeah, I'd grab a calculator. So that's enough of the dB. We got to now talk about isotropic. Believe it or not, the word isotropic is important to you as a radio person. And here's why. Isotropic means having a physical property which has the same value when measured in different directions. Well, that's very convenient to us because antennas send radio energy in different directions. The isotropic radiator is a theoretical antenna. No one's ever built one, nor can you build one. But it's still very important, and you're going to see why in about 4 minutes. It is considered a point source. In other words, it's a dimensionless radio that occupies a point in space. It isotropically radiates, meaning it sends energy in every direction equally, up, down, left, right, in, out, everywhere, totally evenly. It has no feed point or feed line, and it can't because they would distort the pattern. So again, it's totally theoretical. The isotropic radiator produces radiation that is of the same intensity in all directions, so it's a perfect radiator. This theory is powerful. It's used as a baseline. If I'm designing my antenna and I'm going to describe it to another engineer, I need a reference. I need to tell them, here's what my signal level is. Well, compared to what? Well, we compare it to the isotropic. Because it has no loss, all the energy is radiated. That means we can mathematically predict if I'm putting out 100 watts into a perfect isotropic radiator, I can tell you what the intensity of the signal is going to be at any point, an inch away, a foot away, or a mile away. Now, some of you wonder about near field and far field. Well, that's the cool thing about the isotropic. It doesn't care because it's theoretical. So we can tell each other, hey, my antenna puts out 4 dB gain of energy over an isotropic, and another engineer is going to know exactly what I'm talking about. So here's our isotropic radiator, which of course is very fictional because an isotropic is a point source. So the dot would be infinitesimally small, but let's just ignore that for a moment. If I put a certain amount of power in, I'm going to get radiation. Now, the arrow in this case is not the direction of the radiation. It shows us the relative strength. The direction is in every direction away from the dot toward the circle. But the circle's not a circle. The circle is a globe. So you see, it's like radiating in every single direction, not just out toward the edge toward the circle, but out toward the edge of an imaginary globe surrounding the point. If I increase my power level going into the isotropic, the radiation gets stronger in every direction. Now again, we can mathematically predict, because we know how much energy is going in RF current, we know what the electromagnetic field intensity will be near the dot, near the circle, or a mile out past the circle, which again, it's not a circle, it's a globe, so it can be any direction imaginable away from the dot. That might sound very esoteric and unnecessary, But in a few minutes, you're going to see how powerful this concept is, and you kind of have to know about it to understand what a gain figure really means. Or worse yet, what the advertisement really means. So what is gain in an antenna? Let's put up a real antenna. This is an actual dipole. This one, unlike the one that you and I usually put up for ham use, is a vertical dipole. It's way up in the sky, away from the ground. There's no pattern distortion due to ground conductivity. When I put power into it, it's going to radiate a certain amount of energy. The arrows indicate the intensity, but not the direction. Well, they represent the direction of maximum radiation in this case, because a dipole radiates rather strangely. It radiates like this, but those are not two circles. Those are a cross-sectional look at a donut surrounding the antenna. Shield your eyes for a minute. We're going to go outside into the sun. All right. We're going to hang our dipole in the sky. So west is to the left, east is to the right. North is into the page past the dipole. If you wanted to go south from this dipole, you'd come out of the page and hit yourself in the face. Your face is to the south of the dipole. So now you understand how it's oriented, and it's far enough off the ground that there's no ground loss or ground effect. I don't know how far that would be, but let's just say it's a long way off the ground. So I showed you the white arrow. Look at the red one. Notice that the red one is shorter. This is what the circles are for. It is showing you the length from the origin of the antenna to the circle indicates the relative amount of field strength in the radiation going in that direction. If you look really closely, the red arrow is shorter than the white one. So there is radiation going in that direction, but it's a lot less than in the direction of the white one. Now, you might hardly be able to see it. Now there is a red arrow right here, very short. It's short because the circle is so close. That indicates the power level of radiation in that direction isn't even 10% of what it is in what we would call the major lobe out here. Now let's go back to the isotropic. If there was an isotropic right there, and I put a certain amount of power in, I would get a field intensity as long as the dotted white arrow. If I put that same power level into the dipole, my field intensity of radiation is equal to the length of the solid white arrow. What this means, you're standing out here a considerable distance away. I transmit on the isotropic and you say, hey, I'm hearing you at an S2. I switch to the dipole and you say, hey, I'm hearing you at an S4, you must have turned an amplifier on. No, I didn't. What I did is I switched to a dipole, which doesn't throw radiation up and down. Instead, it takes all of this radiation in this area and in this area, and it puts it in here, and it puts it in here. So in this case, the intensity of radiation is 1.64 times stronger on the dipole than the isotropic radiator. We say the dipole has a gain of 1.64 times the power over an isotropic radiator. Now, it only has this advantage in the right direction. If you're up in the sky overhead, you're going to hear a lot less of me if I'm on the dipole, say up here. You're not going to get hardly any radiation, and you're going to wonder who's talking to me. Now, you came here to learn about gain in dBs. So let's go back to the dB chart. Well, we're going to have to modify the chart. There we go. Now, 1.64 times the power is 2.15 dB. So we say the dipole has a gain of 1.64 times the power over an isotropic radiator. The way we would normally say that is my dipole has a gain of 2.15 dB over an isotropic. Usually we would say my gain is 2.15 dBi, little I. The little I means I'm making a gain claim over an isotropic. So you know exactly what I am saying, because I'm giving you a reference. My reference, my standard, is the imaginary isotropic radiator. So you can say, oh, well, that's kind of cool, but you're just saying you're using a dipole. Why don't you just say you're using a dipole? Now catch something. Gain in an amplifier is when the amplifier adds power to the input signal to produce an output signal that is more powerful. But gain in an antenna is when the antenna takes radiation from some directions to focus radiation in a preferred direction. Antenna gain is always from changes to the pattern. Antennas do not increase power, nor do they amplify power. They provide gain only in certain directions, at the cost of less signal in an undesired or unnecessary direction. All right, so let's take what we've learned. Here is the Dunscap Labs Super 2 meter base station antenna. This thing has very high gain. In fact, it has 6 dB gain over a dipole. But if I'm 6 dB stronger than a dipole, and a dipole is 2.15 dB stronger than an isotropic, I can claim 6 dB gain, or I can claim 8.15 dB gain, and I'm not lying. I'm not telling you the truth because I'm not telling you what I'm really telling you, but both of those claims are accurate. Maybe not totally honest, but they're accurate. Because if I call it an 8 dB, you're going to buy it over the guy that claims he has a 6 dB antenna, aren't you? Well, no, you're probably not, because if you look in the literature, I should be claiming 6 dBd or 8.15 dBi. If I don't claim either, you don't know what I'm saying. So that's the first thing you want to look for, especially in the VHF and UHF antenna world. Often, those antennas are rated in dBi, not dB dipole, okay? On HF, they seem to be relatively honest and usually are referencing a dipole. I don't know why the discrepancy, I've just observed it. So that's how we specify gain. And you just ask yourself, well, is it gain over a dipole or an isotropic? And a lot of times you can't get an answer. So that should take care of gain. What's front to back? Well, now we have the Dunscap Labs Super 2 meter beam antenna. This thing has 14.15 dBi gain or 12 dBd gain. Now, the way I would say it, it's a 12 dBd gain antenna. I would just tell you that. So I'm 12 dB stronger than a dipole. If I put 10 watts into a dipole, I get a certain radiation. But if I put 10 watts in this, well, 12 dB, the first 10 dB, that takes me from 10 watts to 100. The next 2 dB take me up 1.58 times in power. So now I multiply the 100 watts times 1.58. I got 158 watts ERP over a dipole. That means the strength in the direction of the yellow arrow, if you were standing way up to the left, the strength my 10 watt radio gave you on my Yagi would be equal to if I had a 158 watt amp feeding a dipole. Of course, in other directions, it's not that great because we're taking radiation from virtually every direction to make this happen. So what's a front to back ratio? Front to back ratio, this one, by the way, has a 20 dB ratio, front to back ratio, means the signal coming off the back is 20 dB weaker than the one off the front. Front to back ratio is a common Yagi specification. Well, what's 20 dB? Well, there's no way there's 100 times the power coming off the back. So it must be 20 dB loss, which was 1/100th of the power coming off the back. That means coming off the back, I have 1.58 watts effective radiated power, which means if you're standing to the right, the dipole would be much stronger than the Yagi. If you were standing off to the left, the Yagi is much stronger than the dipole. So that's what that means, what front to back ratio means. Front to back ratio is how much weaker the transmitter will seem off the back versus the front. It also shows you how much less I'm going to hear off the back than off the front. One last item. I feel obligated to mention this. There are other lobes off an antenna. Let's mount this antenna vertically and look down on it. There's a 20 dB null to the back. There's 12 dB gain off the front. But there are numerous other, and this is just 4 of them. There's many more. There are minor lobes off the sides. When you're swinging your Yagi around, don't get fooled and peak on one of the false rises. Swing it a little bit and make sure you're seeing the peak one. The lower the gain, the antenna, generally, the bigger those side lobes are. A really long boom Yagi won't, the side lobes will be really, really, really small. That is about as long as I'm good for tonight. My voice is almost gone, which you probably can tell. To really fully understand the dB again, go look up DCL 090 series on math and the dB. Don't miss DCL 400. And coming up, I'm going to do, I don't know, maybe 3 or 4 videos on the Smith chart, mostly to help out the nano VNA crowd, but really as a general project, I just want to do it because Smith charts are really rather cool, and they're not nearly as hard to understand as people seem to make them out to be. And I promise you to make good on my promise to explain them in terms that you can understand without big long textbooks and calculus courses. I'm going to do a video, probably more than one, on more tips and shortcuts for the nano VNA. That'll take me to, well, I think I've got 5 nano VNA videos up now. I'm probably going to do at least 2 more. Thank you so much for spending 23 minutes with me. I thought I could do this a lot faster. I'm sorry I didn't. Perhaps if I could breathe, I could have gone faster, but it's a struggle to breathe right now. Anyway, thank you so much for watching this video. If you want to subscribe to the channel, you'll, I guess, get an alert when I produce a new video, which is about 1 a week now. Anyway, thanks for your viewership. You should not be seeing commercials on my channel. If you are, please make a comment that they made you watch a commercial, because I am not monetized. Also, if you have an idea for a video or a question that you can't seem to get answered, or you don't like the answers about something to do with radio or beginner radio, put them in one of the comments. Put a comment in any of my videos, and I will eventually see it and probably make a video on it. At least I'll respond to you. Thanks a whole bunch for watching. See you next time.